In the last video, we saw that you could set up 3 basic electron geometries around the central atom by counting how many clouds there were around the central atom. If you had 2 clouds, you get a linear geometry. 3 clouds, you get a trigonal planar geometry. 4 clouds, you get a tetrahedral geometry. And these are the basic shapes for nearly all organic molecules. Now, when you say geometry, you can think of that as a synonym for shape. So, it's electronic shape. It's the shape of the electron clouds around there. Now, be clear on what an electron cloud is and how you count them. An electron cloud is a bond. It could be a multiple bond. All that counts as one cloud. If you've got a multiple bond, all of the electrons in the multiple bond hang together in a single cloud. So any bond counts as one cloud. Now, another thing it can be is a lone pair. That counts as an electron cloud. And an unpaired electron in a free radical that also counts as a cloud. That one unpaired electron, that one lone electron, can count as an electron cloud. So, for example, suppose you've got a water molecule and you're trying to figure out what the electronic geometry is around the oxygen. How many clouds do you have there? Well, each lone pair, that's a cloud, and that's a cloud. And each bond, that's a cloud, and that's a cloud. So there are 4 clouds there. So this would have a tetrahedral electronic geometry. What if you had this molecule? What electronic geometry would this one have? You're looking at the things that are attached to the central atom. There's a multiple bond. That counts as one cloud. This is a cloud, and this is a cloud. So that's 3 clouds around the central atom. So you have a trigonal planar electronic geometry then. All right. One more. What if you had, well, we did carbon dioxide in the last video. What if you had this incomplete octet structure? Beryllium is satisfied with only 4 electrons around it. Remember, that was kind of an exception. What would be the electronic geometry of this molecule? Well, there are 2 bonds. So that would be a linear electronic geometry. Now, there are 2 more electronic geometries that are not very common in real life. They do occur. You can have 5 electron clouds. And the arrangement there is kind of complicated. It turns out that you have your central sphere, and you would like to put 5 objects on that where they were as far away from each other as possible. Because remember, each of these objects, each of these little sticks, counts as an electron cloud, and they repel each other. It turns out that the best way to do it is to superimpose a linear shape with a trigonal planar shape. The linear shape will go through the poles, and we'll call that the axial positions. And around the equator, you've got the trigonal planar shape. So one of these is going to come out at us, and one is going to go back in. Remember, we're following the organic chemist's convention of drawing a three-dimensional structure. If I have a wedge, it's coming up out of the paper. If I have a dashed or dotted line, it's going back into the paper, and these other ones are in the plane of the paper. So you can picture this in 3 dimensions. The trigonal planar shape that is in here is on the equator, so they call these equatorial positions. And the name of this shape with 5 things around it is called a trigonal bipyramidal. Electronic geometry. Now, what are the bond angles? Well, between the axial and the equatorial, you've got a 90-degree angle. Between the equatorial positions, since it's just a trigonal planar around the equator, you have 120 degrees between equatorial positions. And, of course, between the 2 axial positions, you would have twice 90. You would have 180, because that's a linear. So you have a number of different bond angles in this. This is the most complex electronic geometry that you can have. Let's do an example of a molecule that would have that electronic geometry. Here is a terribly reactive molecule, SF4. Let's do the Lewis structure for it. Step 1, draw the skeleton structure. Sulfur is closer to the center of the table, so I will put the sulfur in the center. Okay, step 2, count the valence electrons. How many do we have? Sulfur is 6, and there are 4 fluorines, and each fluorine has 7. 4 times 7 is 28, plus 6 is 34 electrons. Okay, so step 3, connect the structure. That took away how many? Each stick I draw counts for 2 electrons, so I took away 8. So I have what? 26 left. Now, the next step is satisfy the outside atoms. They want 8. They got 2 already from those sticks. So they each want 6 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I took away 24, but I have 2 left. Okay, dump all of the remaining electrons on the central atom is the next step. You should have your tips sheet, tips on drawing simple Lewis structure sheet in front of you until you get used to this step-by-step procedure. So if I dump those 2, I'll put them there on the central atom. There is my final structure. Let's check out the formal charges. The sulfur in the center has got 6 electrons on the periodic table, minus how many sticks and dots? 1, 2, 3, 4, 5, 6. It's got a 0 formal charge, looking good. And how about all of the fluorines? They're all the same, so we only need to do 1. It's 7 on the periodic table minus how many sticks and dots? 1, 2, 3, 4, 5, 6, 7. 0. So all of our formal charges are 0, so this looks like the structure. Now let's figure out what the electronic geometry for this molecule is going to be. How many electron clouds are around the central atom? Well, each bond is an electron cloud, so that's 4, and then the lone pair counts as an electron cloud, so that's 5 things. So you would say that this molecule has got a trigonal bipyramidal electronic geometry. One last electronic geometry. When you have 6 things, you get an octahedral electronic geometry. And it basically looks like the X, the Y, and the Z axes going in and out of the shape right here. You can say that these are around the equator here, but you have 6 things coming out. All of the bond angles, every one that's adjacent, is 90 degrees. And you still have 180 degrees between the poles. And it's called an octahedral electron geometry. Why octahedral? Octa sounds like 8, and we've got 6 clouds here, not 8. Well, if you draw the basic shape that we have there, and you connect all of the adjacent vertices, you get this kind of diamond shape. I guess if I drew it a little bit better, it might look like this. So you don't show all the lines, just some of them. You get sort of an solid with 8 faces on it, and that's an octahedron. And that's why they call this octahedral. But remember, when they say octahedral, it doesn't mean 8. It means really there's 6 electron clouds there. Here's an example of an octahedral molecule, SF6. If I do the Lewis structure for this, I'm going to just do it really quick without going through the step-by-step procedure. See if you can go through the step-by-step procedure and get the same structure I'm getting here. If you look at how many things you've got around the central atom, you've got 6 bonds. Now, that seems like too many, but remember, sulfur is 3rd row or below. When you have something in the 3rd row on the periodic table or lower, it can handle more than 8 electrons around it. How many electrons does this have around it? Well, it's got 6 bonds, 2 electrons apiece, so it's got 12 electrons around it. It has an expanded octet, which we talked about in the last worksheet. But 6 electron clouds around it, so we will have an octahedral electron geometry. In the next worksheet, we'll look at molecular geometries, which are special cases of each of these 5. You should memorize this table. I'm going to put a box around it. You should know, if you've got this many clouds, this is the geometry that you get, this is the angle you get, and this is the name of the shape. Probably on tests you'll be asked to name the shapes, or maybe pick out the bond angles, rather than draw these yourself.